Let me invite our guest, Professor Zakhidov.
Introduction. Sorry that you have to listen all the details which are not so important, but now I want to thank and introduce Professor Zakhidov.
So everybody knows me.
They don't know you, but I know you from different side. I did not know him before because he is a little bit younger than me, and he spent most of his career in Russia, like I did, but I did in Moscow, and he was in Novosibirsk as a mathematician. But I met him first, and actually, in a very beautiful place, Khiva, in Uzbekistan, in 2015. Also, we were corresponding, where I organized the School on Functional Materials for Photovoltaics. So I encourage you to go to Khiva, Khorezm, Urgench. Those are the places where algebra was invented. And I organized the summer school supported by the International Center for Theoretical Physics. There is such a place, ICTP in Trieste, named by Nobel laureate Abdus Salam. So many famous scientists come, and we spent a couple of weeks in Khiva, and he was actually one of our hosts because he lives there and he has many summer programs. And I envy, my students should envy you because many of you can go support and go to and study there. Anyway, so thank you very much for inviting me here today. I pay back for you hosting me in Khiva, and we become good friends. So today I want to speak about energy and materials for energy. As you know, materials are essence of every important technology. So today we will speak about absolutely new class of materials, which is called hybrid perovskites, organic and organic perovskites. And they are now raising. Probably no one of you have heard about them, or maybe you did because it's a very new thing in solar energy. But before I start, I want to honor the memory of two great Nobel laureates. One of them, Alan McDermott, in New Zealand, a chemist. He was a good friend, and actually our institute has his name now. He invented conducting polymers, conjugated polymers. The plastic, we think that usual plastic is insulated. He created plastics, which can be metals and semiconductors. And after he did this, you mentioned my prediction that under the light, electron can go from conducting polymer to the beautiful soccer ball molecule, which is called fullerene. That molecule was invented, discovered by Rick Smalley, who got his Nobel Prize for this, for discovery of fullerenes. So these two, conjugated polymer and fullerene, are the essence of organic solar cells. And I was working, of course, on that organic solar cells in Japan, in Italy, and always the efficiency was very low. If my student can make something more than 2% efficiency, I said, okay, he can do something. And then 5% was like a dream. And when perovskites appeared, and that was like a shock, efficiency immediately became 15%. That was something that we cannot believe. So today we'll speak about that thing. That is a little revolution happening in that area. Also, they are not stable. So let's speak now about the whole thing which is related with these two scientists. Rick Smalley, when he got his Nobel Prize, he started paying attention to big problems of humanity, and he created this list. It was created in 2004, I think, in his talk. These are top 10 problems in front of humanity. And the first problem is energy. Second problem is water. Then food. When I ask my students in UTD, what do you think is a big problem on this earth? It's all climate change. It is a problem, of course. It is number somewhere here. You see, he even did not put it here, but environment, let's say it's environment, climate change. I will show later that it is directly related with energy. And then this is my grand teacher in science. Ginsburg, Vitaly Ginsburg, Nobel laureate for superconductivity. When I was young like you, 45 years ago, and was joining graduate school, he was giving a lecture like I'm giving you today, and he was saying that the top problems in front of physics, he published that in his book. You see the list of especially important, he was refining these problems, there are many of them. Number one is controlled nuclear fusion, which is the energy. That is the ultimate solution for the energy. That is the energy which is released at sun. We can control it here on the earth. But that dream is too far, it's too big. And maybe it is the future dream. Still, I think I convinced you that 3 Nobel laureates were saying that energy is important. And I'm coming from Texas. Texas in this country was always and will be the state of energy. Energy in Texas is $500 billion business. But what will be the energy of the future? Not oil, which is now important in Texas, or gas, fracking gas. Even now in Texas, they look at the renewable energy. Texas is #1 in the world for the use of wind, the coast. There are windmills. But I'm going to speak today about the direct solar energy. Wind is also coming eventually through the solar effect on the ocean. Now, we are in California today. Who is #1 in the United States leading the use of solar energy? Of course, California. California was, is, and always will be the solar energy state. Because with Schwarzenegger and efforts of other states, here, there are few places in the United States where the solar panels were promoted. There are many companies. But what will be the future type of solar panel? That's what I will be speaking today. Because maybe California will be leading world in the Perovskite solar. And maybe some of you will contribute to that. Every time something new comes, we start in California. I remember I came here 10 years ago. There is one concept of thin solar cell called CIGS. There was company Nano Solar, still developing. But Perovskite is much more interesting than CIGS. Sun. What is sun? Sun is a big fireball, and of course the fusion of 2 hydrogen atoms into helium happens there. It releases so much energy that small portion that comes to the little Earth is huge in terms of what we need and what we use every day. It is 165 terawatts of the light coming to the Earth surface. Is it big or small? Let's compare it to how much we are using today. All humanity, with all the gas and coal, we use in 2007 only 15 terawatts. If you multiply by, this is power, you multiply by year or by hour, you pay bills for 1 kilowatt hour, 9 cents or 10 cents. This is terawatt. Kilo, mega, giga, and then tera. Every time you multiply by 1,000. In 2050, humanity will need 30 terawatts. And we want to have it from alternative, renewable sources of energy. Because by 2030, the sources of gas, fuel will start disappearing. By 2050, they may disappear completely. So we need something which is renewable. What means renewable? You do not consume it. Wind is always there. Water from the rivers keeps circulating. They are not used when you take energy from them. So thus, how much we have there? Wind. The whole potential of wind is only 14 terawatt. I told you Texas is using wind, right? Biomass, 5 to 7 terawatts. you can get of all the gas which is produced by biological species degrading. Geothermal 1.9 terawatt, hydroelectric 1.2 terawatt, very small. All hydroelectricity is important, but we use only 1.2 terawatt. Already in the ocean, tidal energy, the energy of winds, less than 1 terawatt. Altogether will not help to have 30 terawatts which we need in 2050, and in 2100 we need 50 terawatts. Now sun has more than 100,000 terawatts, 165, some people say 120,000 terawatts, but technically, let's say 10,000. This is coming to some reasonable area, not in the high mountains. Still, this is 1,000 times more than we need, right? So what is the problem? We do not know how to use it properly. Now, all the solar energy is converted to electricity by solar panels. You have them here in California, many. And there is good news. I will show you that the cost decreased already 100 times. And the number of installations is increasing in such fast way, so that by the year 2023, we will have 1 terawatt coming from all the solar panels. This is huge. It is comparable to all hydroelectric stations on all Earth, which is great news. However, this again shows, for example, this. This red thing is solar energy increasing. The green, black is coal, gas. You see, they will start declining after 2030. And will, by 2021, you see how there is absolutely little, small amount, where you do not see my arrow. And mostly, everything should come somehow from sun. But how that will happen? We do not know, but the goal is to make it affordable and efficient. Right now, efficiency is not that high. And energy is solution for everyone. 2 billion people in this world are poor in developing countries. And the way to make them rich and to fight their poverty is to bring them energy. There is this special organization. You see, reducing rural poverty through increasing access to energy services. They use biomass heating, which is not absolutely efficient and destroys their nature. So, many problems can be solved. And again, let us look, I think that this is one of the most impressive things which I met in the books when I teach energy. This is how much energy we use every year, this little cube per year. You see, it is 15,000 times smaller than coming from sun. It is good news, we do not use too much. But if you compare with all the resources now remaining on the earth of coal, this is the biggest box, is the coal, the oil resources, is the another box, natural gas resources, this is how much left on the earth, and there will be nothing after that. And we are using this little cube. The big cube is just solar radiation for 1 year. And all the small cubes is everything that is left. We are like these people who are using the resources and burning them, and then there will be no place. Looks like we are in a happy life, but that is not for long. So something should be done. And only people like you who get good education eventually will solve that problem. So, this is photovoltaics, even with the device which has only 10% efficiency. And I told you that Perovskite already do 15. Every student can come to my lab and make 15%. Look, less than 0.1%, this is little cube 1 square. on the surface of Earth, less than 1%, 10 times, can cover all the needs of Germany with 10% efficient solar cell. Or 2, 3, 4, all these squares, okay, this is in Sahara, where the land is not used at all. They can cover all the needs of humanity. Of course, 10% is not much. The good solar cells are 20% now. But still, they are not affordable. And some places do not practically have too much sun. You see, you are in California, here there is a lot of sun. Texas has sun. The red is where we have a lot of sun. Arizona, New Mexico. So we need sun, and we need good solar cell. And this is for the future. We can put little squares all around the Earth, have 10%, and these 6 boxes will cover all the needs. You can say, okay, then what is the problem? Solar silicon is becoming more and more affordable, but there are too many problems. It is heavy. It needs a lot of energy to make it. And it is not aesthetic. Only recently, I always wanted to put on my roof the panel. The homeowners society did not allow because it destroys the roof, and it is not beautiful. Of course, we would like to have something nice, and I will show you that Perovskite can solve that. Now, if you have too much energy, what we do with energy? And the climate is changing, environment is decreasing, with all the pollutions. Energy is the way to get rid of CO2. If you have too much energy, it is very easy by simple chemistry to take all the CO2 dissolved in water, in atmosphere, turn it to methanol. There are books about it. You take CO2, all the clouds, you react it catalytically with CH4, the methane gas, which is everywhere around, and it makes methanol. What is methanol? It's like vodka. Dangerous to your health, but you can burn it in your car. Okay? And that is good source of created artificially fuel, improving the nature, right? Environment. What is missing? Energy. We need energy. We need all these terawatts. Where we can get them? This is the official report from the National Academy of Sciences. You know, the most serious organization in our nation is the National Academy of Sciences, National Academy of Engineering, Institute of Medicine. All of them say that the challenge number 1, make solar energy affordable. Once it is affordable, 165,000 terawatts coming, you can do it. And the big vision is to make it beautiful, simple, aesthetic. We need something like a solar paint. If we can take packet with paint, put it everywhere, it will produce that 10%. We can coat the roofs, the windows, everything. And that will solve the problem. So this dream is pursued here in California already for many years. Everyone trying to make it so in shingle or paint, which will produce electricity. And perovskite, which I will introduce you later today, is probably the given by God solution. Also, there are many problems. It's not stable. And once you have it as a paint, you can do many things. You can make smart windows, solar windows. You can use it as a textile. There are many, many ways to use it in a beautiful type of energy creating devices to charge your batteries and other things. Okay, now let's look what is available. We know that in gas, gasoline, coal, there was one table. This is now the official table of National Renewable Energy Lab about every solar technology and material which was created over the years. So silicon is this blue line. Solar photovoltaics was created nearly a little bit more than 50 years ago in bell lamps. After that, the efficiency was increasing very slowly, from 12 or 16%. Now, the good solar panels have efficiency of 25%. And that is only 4% below the limit, theoretical limit for silicon, which is non-direct semiconductor, is 29%. Even that little 4%, many companies trying to get. Gallium arsenide, which is the pink, violet color, the theoretical efficiency is 33%. In Russia, Alfera, many years ago, was able to get it as 29%, and they use it, it's very expensive thing. They use it in space. And Yablonovich here in Berkeley has his approach to gallium arsenide. So I'm showing you the high end. So this is the gallium arsenide here. All this, 43%, are the multi-junction. 1 square centimeter of that solar cell costs $10,000. They are used in space. Because you put silicon, then you put on the top of it gallium arsenide, you put some other solar cell. Each solar cell converts its solar color from the white sun, and you have 43%, but it is extremely expensive. Now let's look to all this. These are called emerging solar technology. I was speaking about organics. Organics is here. It started with, I said, 2%, and now it reached only 10%. That is what Alan McDermott and others were doing, and that was our hope. Then there is so-called disolar cell. The highest efficiency is about 12%, and it stopped. It was impossible to go beyond 12%. And then there are quantum dot solar cells. So all of these emerging things are here. And you see in 2013 something appeared here, and it keeps increasing very steeply. The derivative of it is very high. This is perovskite. These perovskites are our hope, and this is the topic our talk. So multi-junction is $10,000, others $1,000. Thin films, these are the thin films. They are low efficiency, green ones, $100, but not expensive. They are used somewhere, but also not very good. And this perovskite, or desensitized, is cheap, it is this one, but efficiency is low. We need new materials. Silicon will not do it, for many reasons. Now, many of you think that solar is what is the solar plants in Spain and other places. This is not direct conversion to electricity. This is when you have many mirrors, concentrate mirrors on the top here, and there is an engine, Stirling engine, boils water or other liquid, generate, creates electricity. This is not the way. This is what people do in Germany and here in California. You put on the roofs the solar panels. And that is what I say is also not good thing, because it needs maintenance, needs silicon. But let's look to silicon, because not of any of you are physicists here, so I will remind you. In silicon, the thin sliced silicon plate, you create p-n junction. This p-n junction, when the light is coming, separates carriers. Plus goes one side, minus goes the other side, and you have the circuitry. But it is made of many layers. That's why it is so expensive. And it is, actually looks like this. You see, you have electrodes which are made of silver, it's expensive. And you have the bottom electrode, and this thickness is about 20 microns, the smallest. When we will speak about perovskite, it will be 200 nanometers. 5 times less than 1 micron. Silicon is about 25 microns. So it's sort of heavy, and there is a lot of material there. That's why it is costly. Okay, maybe I will not show you this, but still, maybe this is important. This is so-called energy diagram of the p-n junction. The light comes, takes the charge from one zone to another, then one charge goes down the slope, these like bubbles go up, and you separate the charges, and this is the voltage. You need p-n junction. To make p-n junction, you put silicon in the hot furnace, and you heat it. And you have dangerous gases that should be there. So this is big technology. Okay? Now let's go back to what I loved since last 30 years, organics. In organics, that was pioneered by him, and also fully ran. You have two very thin films. These films are extremely thin, 100 nanometers, another 100 nanometers. You hit by light. Light excites so-called excitone. This is the coupled pair of plus and minus. They migrate to the interface and separate. That's what I predicted, and we found it in this system, which is used. P3HT C60. Many companies appear, they start doing this. Okay, and then, why it is not doing, okay. So in this material, look, we need to generate excitone close to interface. And excitone can run very small distance, only 10 nanometers. If it is not within 10 nanometers close to the interface, it will disappear. So we need to create the system, and then the charges go back to electrode, and this is only 100 nanometers. So both of them to 100 nanometers. Because in organic material, the properties of the material limit the diffusion of excitones in charges. They are poor. That's why efficiency is low. I will quickly go, I will show you the process. So what you do, you shine light. These are the coupled pair. They diffuse very short distance. Then they separate. Then they separate further. The charges travel another 100 nanometers. And that is your solar cell. But you need many interfaces. To have many interfaces, you need to create something like this. Everything is interface. And the distance is nanoscale. That's why nanotechnologists like me can do this. You need nanotechnology. In perovskites, as I will show you later, you do not need all that. So here we need bulk heterojunction, and all this emerging, they were here. You see UCLA, they contributed, everywhere UCLA, they contributed to these numbers which are all below 14%. And what happened recently? DOE said, this is second generation, 14%. This is silicon, but silicon now improved, first generation. Third generation should start from 20% and go very steeply so that it will cost less than 20 cents per watt. This is a dream. People did not believe to this dream because there was no material to hit this point and start going up. But this diagram was created as a dream. Now this dream, fortunately, has chance to happen because perovskite goes right here. As I told you, it starts from 15 and 20%. And the slope is very high. Okay, so what is this? This is this nice material. It's like a jewel. See, it's made of little diamonds. And it started raising like vertically, nearly vertically. These are all sorts of reports. This is all previous technology. And this keeps accelerating. This is this structure. So where it comes from? This is another thing showing how amazing it is. So what is perovskite? Perovskite is the crystal that looks like this. Look, it has three components, A, B, X. X is usually iodine, bromine, chlorine. It's halogen. That's why they call organohalide. Where is organics here? When many years ago, Gustav Rose found the first perovskite. It was calcium titanium oxide tape. It was found in 1893. It was supported by Russian mineralogist Lev Perovskite. Therefore, it is called perovskite. Perovskite gave money to this German, so he put his name on the mineral, which is beautiful thing to do. And then another German found the structure. Structure is quite complicated. You see, you have, this was calcium titanium oxide. You have this tetraoctahedrons, and in the cage there is another material. So material about which I'm speaking today is quite different, because the cages is filled with organic molecule, not with titanium or calcium. It is filled with methylamine, CH3NH3. And it is a dipole, it is electrical dipole. It has minus end and plus end. There is enough space here. So this type of molecules was found by serendipity by another German, his name is here, Dieter Weber. He described CH3 and H3PBX3 in 78, a long time ago, but nobody paid attention. It was sitting somewhere in the lab. It can be created from the solution like a kitchen salt. Basically, this is the same ionic crystal as sodium chloride. Sodium chloride is your kitchen salt. You put it in water, it dissolves, and you can taste nice. This thing just has three elements. Lead, you have something as a chlorine, iodine, 3, but it is not simple cubic structure. It is, you see, of course it is cubic, but then there are other elements here. All this makes it unique. There are many, many unique properties. Best superconductors, ferroelectrics, non-linear optical materials have this crystal structure. So when people say perovskite, it is not only one material. It is type of the crystal lattice, more complicated than cubic lattice. It has these little diamonds in the middle and the cages. You can also look at it in a little bit different way. You can say that, you see, there is a way to say that lead is around, iodine in the middle, and organic molecule is in the middle. This is called methyl ammonium lead iodide. They call it MAP, methylamine lead P iodide. And not any material can become a perovskite. Another guy, another German, Goldschmidt, he found that there is a special relationship between the radiuses of these atoms, A, X, and B. It should be in this range. These are some examples. There should be certain valences, the neutrality of charges. So any of you can take, there are about 1,000 elements that can get into this formula. And there are many organic things that can get into the cage. Maybe one of you will find a perovskite which is magically stable. People are trying to do that. They're trying to make alloys. They have double perovskites. They mix iodine and bromine. You know, there are, you can mix. You can put SN instead of lead, and this is the range, as I said, between 0.8 and 0.1, which can make this nice structure. You see, all these are the halogens. This is what people now use. These are organics that are used, but you can use others. And you can make your own perovskite. What is so good with perovskite, you can make them just in the solution. But instead of water, you use organic polar liquid. DMSO and other liquids are easily dissolving this material. So in what I said, this is semiconductor. When you make this, the valence and conduction are sitting one on the top of the other. That creates very good optical absorption. They are very colorful. And that was the attractive point for one student like you in Japan, graduate student, or even he was a master student. His name is Kojima. This Kojima made a solution, colorful solution, and what he did, he decided to use it in solar energy device. Nobody did before. I will show you what type of devices he used. If any of you, anyway, this shows that you can have different band gap, means different colors, green, red, and there are so-called layered perovskites. You see these little, like diamond type structures can be separated by bigger molecules. You can have 2 layers, 1 layer. All that creates a big family of perovskite. So now let me show you how the nature creates photosynthetic reaction in leaves. In the leaves, the light is absorbed in chloroplast, energy is transferred, and then there is the reaction, which is called photosynthesis. So there are different steps. This is like antenna, it absorbs light, then the charge transfers and separates. Grätzel used it in dye-sensitized solar cell. He used some colorful material as a dye. This was the dye. The dye absorbs light, creates exciton, and then the charges are separated. Okay? So Grätzel, which is called Grätzel cell, used this pigment, colorful dye, and he soaked it into titanium oxide nanoparticles. And that was analog of photosynthetic. So what the Japanese guy did, he said, okay, let's use as the dye here. This is the silicon solar cell. You see it has p-n junction. In Grätzel cell, you have the dye, you excite it, electron goes to titanium oxide, and the plus charge goes through the electrolyte to the other side. This is how they look like. They are beautiful. In Italy, these Italian people make panels which they can put in the windows. The efficiency is very low, but they look like leaves, nice colors. So what Japanese guy did, to mimic this reaction, he put perovskite. Now you know the structure. Instead of this, he put perovskite on titanium oxide. His name is Akihiro Kojima. In 2009, anything that is colorful, my students use green tea, cherry leaves, rose hips, anything which is colorful can be used in Grätzel cell as the pigment. He used perovskite, and it was a success. But it dissolved in the electrolyte. He did not know what to do with it, but they published a paper which was beginning. Then other researchers started doing stuff. And then in 2012, several papers appeared already. Grätzel himself started doing that to stabilize dissolution of that pigment in Grätzel cell. I met him in Turkey in 2013, immediately rushed to the lab, and students start synthesizing because these materials, you cannot buy them. And this is the emergence. The first solar cell was 3.8%, still twice higher than organic. And now, NRL has 23.1. In my lab, you can easily build, in my UTD or ITMOR lab, 18% efficient solar cells. And we are not trying to increase efficiency. We are trying to find the new physics and new phenomena in this material. It is full of magic. You see, this is the history of perovskite solar cells. And now many, many labs, thousands of researchers are trying to improve this technology. This is how it looks like. Instead of putting the titanium oxide, you just put perovskite absorber. This is SEM image. This is scale of 500 nanometers. And they look like little crystallites. They're not very beautiful. It's a dark film. And this shows the different colors of different type of perovskite. You want iodine perovskite. It is dark brown. It gives the highest efficiency. We work with nearly transparent, which is bromine. Let me show you how it works. It works somehow similar to organic. I describe you. Look, there are two scenarios. You create carriers, they create exciton, and then this couple travels long distance, not 20 nanometers like in organic. They go for microns. This is one unique property of perovskite. Nobody knows why it happens, but the carriers can travel long distance. Not only carriers, but also excitons. And then you separate them, and that creates the charges. Okay? And the energy of the coupling is very small. It is around the energy of the room temperature. In another scenario, you create without any exciton carriers. They also travel long distance, and then they separate. And that is another scenario. Anyway, so what is the secret of success? Secret of success is that by some magic, which people are still trying to understand, this material has very high optical absorption. It looks very colorful and beautiful, like a gemstone. And then it has direct band gap, which is close to so-called theoretical limit of solar cell efficiency. And then the mobilities, means the speed with which carriers travel, is quite high. And then the defects which can stop the carriers are not effective, they're shallow. So carriers are protected. They are not trapped. Nobody stops them. They go and they separate. And also the diffusion length is more than 1 micron. Everything can be done from solution. These are most important things. But what is the problem? This is the problem which maybe some of you will solve. It is not long lifetime. This is missing. You want to paint the roof, if the rain comes like you had yesterday, the storm, it will wash away all the perovskite from your roof. Moreover, it has lead. Lead is dangerous. So people are afraid. If you will have too much lead coming from your roofs, that can be dangerous. It is toxic. So if somebody asks you, you know now, there is evolution, there is new material, it is extremely efficient, but it has toxic lead, and it is not stable. Of course, we can protect it. We can coat it with plastic. We cover everything with plastic, even this. We do lamination of plastic. Okay, that was done. But if you put metal as electrode, silver, iodine reacts with silver, and silver turns into the silver iodide, which is insulator. Anyway, it is close to the theoretical limit of 33%. This is the shock. And it has the good energy gap, it has good mobility. I will start to finish soon. I will not speak about all the physics thing. What is nanotechnology? If you will come to my lab, you will not do just the film. We will do the film which has nano imprinted, beautiful nano gratings. These nano gratings improve many types of effects that we expect. It absorbs better light, The carriers diffuse 35 times better. Recently, some of our students already, we got patents on this. We have special way to put a little droplet, rotate it, and make very nice films of these perovskites. And we can do different periodical structures, which not are good only for solar cells. We do solar photo detectors, we can do them to lasers, because these devices, contrary to silicon, silicon you cannot turn into the lamp. You cannot make a laser of silicon. This material can be as a solar cell, or if you do it in a different way, it can become a screen, a bright lamp, or a bright display. So this is the beauty of the material. It has, what we are doing, we are putting little particles here, noble particles. For example, gold. Nanoparticles accelerate the separation of charge by the resonance effects, like a little antenna. This is just demonstration of how rich can be the field. Or, like here, you see we put silicon nanoparticle into perovskite, and we can increase. This is the performance of solar cell, and we can easily get 2% more by putting little particles inside that 200 nanometer layer. And recently what we did, as one of our projects, we created the device which is dual function. What means dual function? This is the picture that shows that, let's say you have this, and during the daytime, all these letters or arrow, they generate electricity, they are solar cell. If there is no light, they turn to the lamp, to the display. So the same system can be either solar generating, electricity generating material, or the electricity which is generated can be used to create light. We call it double function. You see, it generates light. But if you put light on it, you generate the electricity which you see as the IV curve. It's not very bright light, not that bright like this lamp, but you can do both. You can generate voltage, current, or you can have a bright spot, which is a dual function. We published, people are happy. Moreover, we can put it as a paint in the devices. This is this function. You either generate carriers or you inject carrier and generate light. Can you do it with usual solar cell? Not. So this has additional functions, and I think it is the time to stop here. And this is one of our dream devices. We want to combine wind turbine, solar heater, and all these colorful things here are the perovskite solar thin film coating in a combinational device which integrates solar heating, wind, and solar electricity without complicated maintenance. This is one of our future projects. So this is what I tell to you. Be a scientist, create energy for the world, and to do that, come to our Nanotech Institute. This is Alan McDermott Nanotech Institute in Dallas. We create all these nano structures, screens, carbon nanotubes. By the way, we found that carbon nanotube is the most stable electrode for perovskite solar cells. Iodine does not degrade carbon. Iodine and bromine and chlorine degrades all the metallic electrons. It is expelled from perovskite. But carbon only improves the quality. So, and this is my team, funding, Ray Bogman. This is the group that created the nanotubes. And this is what Alan McDermott said. He said, science is people. Science is not equipment, not funding, not projects. Science are you. Science are the young people who like Kojima, that student, are fearless to put something which other good scientists even do not think about. From 78, Perovskite was sitting somewhere. Nobody other than a young student stick it into the Gretzel cell and made a solar cell. And then the revolution started. And I have the project in new laboratory which is called Perovskite Lab in Petersburg. It's called ITMO University in St. Petersburg, the old capital of Russia, beautiful city. You see, we have this complicated device. And the team invites you. In Russia, there are special programs for what we call minorities and diverse students from Asian country, from China, from Brazil. You just go to ITMO University and you apply. One of my students already is doing the master degree. We go for summer research. So there is summer research in UTD, which is called REU. Some students come to me this morning and I told them they can apply. Or come to our lab in ITMO University. This was taken after my award 2 weeks ago. And this is my student who became the member of this international team. She joined ITMO as a master student. So, I think I will finish here. I hope that you will ask at least one question.
Well, let's first thank you.